All right, so I want to review a little bit about Bronsted-Lowry, the theory of acids and bases, because we've talked about Arrhenius and we've talked about Bronsted-Lowry already, but to kind of review, remember with the Bronsted-Lowry definition, we're focusing on an acid being a proton donor and a base being a proton acceptor. And remember, we can use the word proton interchangeably with the hydrogen ion, or H+, because remember, a hydrogen atom is really, really simple. The most common isotope of hydrogen is called protium, and it has no neutrons. So all it is a single proton and a single electron. And if you leave that electron behind, a hydrogen ion is just a proton. So I remember this just to help me, because I'm all about trying to make it easier on my brain. Oh, come on, pen. There we go. Is that D, acid is the proton donor, because my brain likes alliteration. So that helps me identify then the acid based on a Bronsted-Lowry definition. And so we can see, you might know already that hydrochloric acid is definitely going to be defined as an acid, but when you look at the reaction through the lens of the Bronsted-Lowry theory, we see it as a proton donor. It donates that hydrogen to the water molecule, it makes our hydronium and then the chloride. We can see our base here as ammonia, and I would definitely recommend putting to memory that ammonia here, this NH3 molecule, is a base. It'll just kind of help you in the long run. So one of the problems here that we see is that if you put ammonia into water, its pH will definitely change, showing that it's basic, but it doesn't fit the Arrhenius definition. But if you view it through the Bronsted-Lowry as a proton acceptor, accepting a proton from ammonia, we can see then that water can act as a base in one situation and an acid in another. We can see how we generate those hydroxide ions that would be how we would define it through an Arrhenius. So the Bronsted-Lowry theory of acids and bases is kind of an improvement or an expansion on the Arrhenius theory in that it doesn't depend on water for the definition, and it does broaden the definition to include some chemical substances that we later found out definitely were bases but didn't fit that original definition. Another way we can look at that is more visually using like ball and stick models, and sometimes that can help our brain. So look at how in that first reaction we have the hydrochloric acid behaving as a donor. It donates one of the little white spheres to generate that hydronium ion. And look at our second equation here, how the ammonium acts as an acceptor. And the reason ammonia can act as a proton acceptor, as you might remember, you can tell this trigonal pyramid right here it has this lone pair of electrons right here on the top of this highly electronegative element, highly polar, and so it has an attraction then for that little proton, and so there's a pull there, and so it acts then as an acceptor of protons, and then we generate the ammonium ion. You'll recognize that ammonium ion right here from your polyatomic ions list. Another thing I want to draw your attention on this slide is the differences in the arrows here. Between these, that's not a coincidence. This arrow is written the way it is because hydrochloric acid is a strong acid. So because it's strong, it's essentially not reversible or reversible to a negligible degree. It 100% dissociates. However, ammonia is a weak base, meaning there's only a certain percentage, and the weaker or the less that percentage is, but a certain percentage that actually will accept the proton. So if we were looking in a situation of an aqueous ammonia solution, what we'd find is just a few of these are actually in this form. And so we have to have that reversible arrow. So just to kind of review our acid-base theories, we started out historically with that Arrhenius. This is one of our first scientific definitions of acids and bases beyond our original, like, oh, some are sour, some are bitter. So with the Arrhenius, they are direct contributors of either a hydrogen ion or a hydroxide ion. So they have to directly contribute that into solution. So like HCl, sodium hydroxide. Because of the way they dissociate when put in water, they are directly contributing hydrogen ions or hydroxide ions. It requires that we be talking about dissolving in water, and it requires that we're directly contributing to those concentrations, which limits it. Our Bronsted-Lowry definition, which we're going to add here, you'll notice encompasses the Arrhenius. what that means is that if something can be classified as an Arrhenius acid or base, it automatically can also be classified as a Bronsted-Lowry, but it doesn't go the other way. Now, maybe it's both, but maybe not. So for Bronsted-Lowry, we define it instead as a proton donor and then a proton acceptor. I'll abbreviate that. So yeah, HCl can be defined both ways, because if you're Arrhenius, you're also Bronsted-Lowry, but something like ammonia can act as a base and indirectly contribute hydroxides in an aqueous solution, but not directly. And so if you can be classified as an Arrhenius acid or base, you are also within the Bronsted-Lowry, but that isn't necessarily true the other way around. Ammonia is definitely a base, but not under the Arrhenius theory, not under the Arrhenius view. So this is an expanded view that kind of fixed some of the limitations of the Arrhenius theory. So let's do a quick practice. I'd encourage you to pause the video and attempt to classify each of the following compounds as a likely Bronsted-Lowry acid or base. So pause the video and think about it a little bit. Now, I kind of think that these are a little bit challenging because they require quite a bit of background knowledge. So one thing that might help is to consider Lewis structures. So I'm going to add the Lewis structures to that. And if you got stumped, then I'd encourage you to right now that you can visualize the Lewis structure, pause the video again and try to determine if you think it's going to behave more like a Bronsted-Lowry acid or a Bronsted-Lowry base. Now, again, still, I do think there's a level of background knowledge that's needed that sometimes our textbook doesn't appreciate. The textbook's written by chemists, and they forget that when you're at the beginning, you can't automatically see in those chemical formulas or in those structures. So here's some tips for that. So taking a look at this, now I just told you that ammonia acts as a base. And so you might be automatically tempted to jump in here and be like, oh, that's going to be a Bronsted-Lowry base. But, okay, so let's kind of think Lewis structure here. NH3, and there's our little dot dot, ammonia. And I told you that it can act as a protein donor because of that lone pair there at the top that can accept the proton. Now, if you look here at the Lewis structure, you'll notice that there is no lone pair there at the top. It's actually already been taken by a proton. And the reason this is easy to kind of get confused, because you see that NH3, one of the things you have to remember is one of these H's has been substituted by a little carbon. We would call it a methyl group. So it's been substituted. So there's no place here for this to act as a proton acceptor. However, it's easy for me to envision that this could become, I'm going to clump these hydrogens together for simplicity, could become this, since we know that this structure is fairly chemically stable because it reminds me of this chemically stable structure. So based on that, it seems to me that this could act as a proton donor and therefore is most likely to behave as a Bronsted-Lowry acid. Remember how I remember donor acid. But I do have to do a little bit of thinking, and I have to think about what kind of structures. So if you see an NH3, don't automatically assume base. Stop and consider, are all 4 of those spots filled? Because if they're all 4 filled, if we have that nitrogen bound to 4 things, or even like that, if all of those spots are filled, there isn't that lone pair. And you're usually going to see that little positive there. So that positive is an indication that it's probably filled. Again, quite a bit of background knowledge here. So let's jump down then, down or over, I don't know. Let's go over. Okay, so when you look at this, you might notice there's not a single hydrogen in this entire formula. And so maybe that gives you a hint. And that hint is correct. It's hard to donate something you don't have. And since this doesn't have any hydrogens to donate, it's unlikely to act as a Bronsted-Lowry acid. However, this little structure here, this oxygen single bonded to something with a negative sign, these are kind of a hint. In the same way that this is a hint at something, these are kind of a hint for something. Because as we see with even just like water, oxygen is fairly stable to have a hydrogen on it. So if you have this situation, negative, which is what this is indicating, we have, this is a negative sign, we have an H plus opportunity to bond to that lone pair. Here, I'll put the little lone pair sign, or that's my sign for it, not a real. So this has actually 3 places where it could accept a proton. So this is most likely going to behave as a proton acceptor or a Bronson-Lowry base. And in fact, it can actually accept a proton for each. And if you recognize, you might not, and that's okay, if you recognize that chemical formula, it's the PO4 here, but with the 3 hydrogens, that is the chemical formula of phosphoric acid. So it can definitely, this chemical here, this phosphate, can act as a Bronson-Lowry base and accept multiple times, multiple protons. So we have a similar situation here. We have that the lone pairs on the oxygen with a negative. So that's one of those hints that we're likely to accept a proton. We could accept a proton right there and make, that's just a really stable chemical structure, that oxygen single bonded to something on this side and single bonded to hydrogen with 2 lone pairs. We see it in a lot of things, even like water. So I would predict this is going to behave as a Bronson-Lowry base. And then over here, what do we have? So we got lots of oxygens, but notice none of them have that very structure we were talking about, where we're like, okay, we've got multiple lone pairs and that negative. So they don't really have room. They have pretty full valence shells. And though they could attract a proton, they don't have the valence room to keep it. So over here, take a look at this. Isn't this the opposite of what we were talking about here? We were like, oh, this could accept this. Couldn't this donate it and become that? Well, it could. And in doing that, we would get a really similar structure to what we're seeing. Oxygen with 1 single bond and 3 lone pairs, and then a negative charge. And so I would predict that this chemical here is most likely going to act as a Bronson-Lowry acid because it's a proton donor. It could donate that proton. So what we're seeing here in this slide is some reminders of certain chemical organization, certain structures at the atomic level that can hint toward their chemical behavior. So if you see anything, these could be H's, they could be other things, but we got that nitrogen with the lone pair, that's more likely to behave as a base. If it's full, we make it full, and it has that positive charge, that's more likely to behave as an acid. If we have the oxygen with 3 lone pairs, single bond, and a negative, that's a hint we could accept a proton there and behave as a base. If we have this, depending on the structure, it does get a little complicated as we move on in chemistry, but just depending on what this other thing is, we could donate to become this fairly stable structure. So I understand there's a little bit of background knowledge. You have to think a little bit deeper than just looking at them. You have to think like, is that structure likely to donate, or is that structure likely to accept? And remember what we're donating and what we're accepting. We're donating protons, we're accepting protons, and that's really another way to say that little H plus.